is how to solve these more complicated versions of pig that have multiple dimensions. So before it was one-dimensional, now it's like 3 or 4-dimensional or whatever. And we're starting with this question: what order should we learn in? Should we learn? And I'm talking about with respect to the time. So maybe it doesn't matter, or maybe you want to learn one first or the other first. Let's take a look, and let's reveal what people said. Okay. 6 people said learn them all at the same time. That would be sort of like the classic iteration. You just think of time as a parameter. But 8 people said we can learn the ones where there's only a few turns left, and that is the correct answer. And the reason is we kind of know what happens when there's 0 turns left, and we can kind of base on that. So if we go to our thing, our Blackboard, let's see if I can open this up. Oh, here it is. So we had this this setup. We have B, C, and T. B is how many points we've banked already. C is the current amount of points we have. And T is the number of rounds that are remaining. I like to count down with T. So T equals 0 is like you're done, and you start at T equals 5. That way we can sort of like build up to infinity if we want to. And we had this initial condition that B, C, and 0 is something that tells you what's going on when there's 0 rounds left. Well, the nice thing is that if you know BC0, then V pi of BC and T equals 1 will be given in terms of the T equals 0. Given in terms of T equals 0. And this makes sense. Like if you know the value when there's 0 rounds left, then when there's only 1 round left, you know exactly what's going to happen on the next round, right? And in fact, if you get to 50 points, then you're going to win. And if you don't get to 50 points, then you're going to lose. So like doing it at time T equals 1 is almost exactly the same as what we've been doing so far, where there were no time rounds. But this pattern continues, so this is the reason it's important to notice, is that V pi of BC T equals 2 depends only on T equals 1, given in terms of T equals 1, and so on. So there's this like arrow of time that you can sort of build up. If you know what happens at T equals 1, then you can use that to find out what happens at T equals 2. If you know what happens at T equals 2, you can use it to find out what happens at T equals 3, and so on. And so by doing this, we can sort of take what we did before, and it becomes a little bit easier. So you don't have to do like iteration over all of them. You just do iteration over the t-axis one time, and then you've got it fully solved. And to show you a little bit about what this looks like, I fully coded this up. So here it is. Here is the one-player multi-round pig. And here's what the code looks like. Well, yeah, I guess we'll go through the code in a little bit. Let's actually look at the results. So here are the value functions at various times. And here I made the maximum, I made it 50 points. And I said you need to get 50 points to win the game. And so at T equals 0, that means there's no rounds left. If you have less than 50 points, you just insta-lose. Like you're going to lose the game. You can't, it's hard to see, I guess, but at 50, there's one blue dot exactly at 1. So if you get to 50 points, then you win the game. This is at T equals 0. And all of this is plotted, by the way, with thinking of the beginning of the round where C equals 0. So you have no current points. You've started the round, and the B is the number of bank points you have. So if you have 50 or higher, you immediately win. If there's no time left, then you immediately lose. And knowing this time 0 on the blue curve, you can fully calculate this orange curve, which is the T equals 1 curve. And the T equals 1 curve says when you have 1 round left, you're trying to get to 50. If you can do it, you win. If you don't, you lose. And so the T equals 1 is calculated in terms of T equals 0. In fact, I can also show you down here what the optimal strategy is. So when we go through this code, you'll see what the optimal strategy is. This is the optimal action as a function of the number of banked points and current points. And what this line is showing you is that you should roll again unless you have enough points to win the game. So if the banked points plus the current number of points are less than 50, you should roll again. If banked points plus current points are greater than 50, then you should stop. So this blue region over here is 0, so you got to stop. Over here, you roll again. So very boring strategy. And the interesting thing is going to be what happens at T equals higher numbers. You guys with me so far? Any questions or comments about this this game or the rules? I'm kind of assuming you remember the rules from last round or from last class. Okay, so this is the sort of like ladder we're going to build. We're going to solve t equals 0, we're going to use t equals 1 to solve t equals 0. We're going to use t equals 2 to solve t equals 1 to solve t equals 2, t equals 2 to solve t equals 3, and so on. So we're going to like build our way up. And then, at the end, we're going to see that with 5 rounds, starting at 0 points, which is a regular way to start, you have about a 50-50 shot of winning the game or not. So if you play it optimally, then you will win about half the time and lose about half the time in 5 rounds to get to 50 points. Okay, any questions or comments at this point? Okay, so let me show you the code a little bit. Okay, there's some fancy stuff, but I want you to focus on, for now, let's focus on, actually, okay, let me show you some of this. Like, this is like a bit of a coding hack. Is I'm doing these kinds of things. So this is what we left off last class with, which is what happens at time t equals 0. And here I'm telling the computer at time t equals 0, what you should do is you should take the 2 entries b and c, and you should give 1 if b plus c is greater than the target and 0 otherwise. So this inequality in brackets will get evaluated by the computer, and it'll give 1 if it's true and 0 if it's false. So this is the nice way of implementing what was written on the board last time. This thing over here. It's exactly this. bc 0, it's 1 if b plus c is greater than 50 and 0 otherwise. The thing that is a little bit tricky is there's a new command that we haven't seen yet before, which is this command called np.indices. np.indices. And np.indices, what it will do is it'll make sort of b's and c's in the right way so that you can do this kind of thing. And basically that's what it does. To explain it a little bit more, I wanted to sort of show a really simple example. And so that's what this little example is here. So I made an array that has 3 axes. It has 1 axis of size 2, 1 axis of size 3, and 1 axis of size 5. So that's what it looks like. Don't worry about what's in it. It just has a 2 and a 3 and a 5. So the 2 dimension is there's this copy and that copy. That's the 2 dimension. The 3 dimension is there's 3 rows. And the 5 is there's 5 columns. So this is a 2 by 3 by 5 array. And the thing that you can do with arrays in NumPy, we've sort of been doing this already, but without being super explicit about it, is that if you feed in 3 numbers as an array into this thing, it will pull out those entries for you. And so to sort of show you what I mean, I made this sample size thing, which is 7 by 11. And I just made x, y, and z to be random numbers between 0 and 2, 0 and 3, 0 and 5, all of sample size. So each of x, y, and z on their own are 7 by 11 vectors. Let's print out x. So it's an array of size 7 by 11. It's got a bunch of 0s and 1s, because x is either 0 or 1. What about y? Well, y is either 0, 1, or 2, another 7 by 11. And z is 0, 1, 2, or 3, or 4. There's a couple 4s. It's also 7 by 11. So I have these 3 7 by 11 arrays. And this is the surprising thing that I think not everyone realizes you can do in NumPy. You can ask for, take an array, and as long as you feed in x, y, and z values that make sense in the array, you can ask for a of x, y, z. And what it will do is it'll take the x values, the y values, and the z values, which were all valid things to ask for, and it will plug them in and tell you the values. So this will tell you the value of the array A, which has 3 axes, at x, y, and z, and so it'll output a 7 by 11 array with what are the various inputs. So for example, I guess I got to print all the x's, the y's, and z's. Let's do it like this. F z equals x equals and y equals, like that. So for example, the very top corner is x equals 1, y equals 1, and z equals 0. So if I take the entry 1, 1, 0 from the array A, that will be 16. And if I take the next entry over, x equals 1, y equals 1, and z equals 1, the 1, 1, 1 entry is 21 in the array. So this is sort of like pulling out all the things in the array. And you can do all sorts of funny things, like you could like set all these to 2. Now, anything that is in this array, like anywhere there was a 16, a 21, or a 6, it got set to 2. Actually, why don't I set it to like -1, and we can see where have we tortured the array A. So now I've set a bunch of things in A to -1. If I say print A, it'll have a bunch of -1s in it now. So all the ones that were accessed with x, y, and z got set to -1, and then there was a couple that were untouched by my random hodgepodge. So what is the point of all of this I'm saying is that you can access entries by doing these slices and feeding in arrays. So the arrays have to be arrays of integers of valid inputs, and then you can access entries in the NumPy array. The reason this is exciting is because there is a command called np.indices. So instead of making them randomly, if I do xyz equals np.indices and indices, okay, then what will it give me? It gives me these nice arrays. So remember, the array, the shape of the array we're looking at, it's 2 by 3 by 5, 2 copies of 3 rows by 5 columns. And the np.indices array generates some x's and y's and z's that look like this. And the x value is always telling you where you are. Are you in the top or the bottom? The y value tells you what row you're in. Are you in the top row in either picture? And the z tells you which column you're in. And so by using these things, you can access all sorts of things. So you can say like a of x, y, z equals, let's make it x plus y plus z, the sum of the entries. Okay, and now I've set a so that every entry is the sum of the entries. So it has this nice diagonal flavor. Or you could say like, make it the sum of the entries plus 2 if x is bigger than y. So you can do any sort of like weird formula you can do, and it'll do it. So that's the np.indices command, which is a fancy version of the array slicing we've been doing so far that works for multi-dimensional things. It's a good trick to know, and it's one I wish I knew earlier. That's why I'm telling you now. This will, if you're good at this, you can really avoid using for loops in a lot of your work, which can make things a lot faster. Any questions or comments about the np. Yeah.
It's kind of deceiving when you print it, but does it allocate all that memory for all the indices, or does it generate it on demand?
Oh, that's a great question. I actually don't know the answer to that. The thing, so NumPy is actually written in C code under the hood. So anytime you write a NumPy command, what happens is there's a C program that runs, and then Python like just calls that C program. And as a result, basically anything you do in NumPy, no matter how stupid, will always be faster than doing it the Python way. It's just Python is not like compiled, it's like interpreted. So it's like, okay, this is like not 100% true, but like within reason. And so anytime you can do something in NumPy like this, it will definitely be faster than the sort of the Python alternative. And that's part of the reason the for loops are slow. Like when I say for loops are slow, I mean for loops in Python, specifically written with Python things, those are slow. There are ways you can like make for loops happen faster in Python by actually using C. Okay, and this is like a skill. This is like if you do like neural networks and stuff, this kind of skill is really important. So I'm trying to slowly build you guys up to it. Yeah, great question. Anyone else? Okay, so back to the code, thing we actually care about. All of this to say, okay, you make B and C the indices, and then you feed that in. So B and C are technically some big arrays, but they have the property that they're always the values that you want, and then you can feed in this kind of formula. Okay, fantastic. All right, what else did I do? Okay, so I made B and C max and T. I made V is our value function, just like from before. And then over here, I made the rule for the value function, which is exactly the same as the rule we had before. V of BCT is the maximum of rolling again or staying. It is inside a loop so that T is an actual number, and B and C are these arrays, just from np.indices. And that is exactly like we had last class. So, and that's like the rule for the Bellman equation, right? If there's two actions, half of the Bellman equation says the value function at some state S is equal to the maximum over all the actions you can take of the Q function, Q pi of S A. In this case, we have two actions. We can either roll again or we can stay, and that's what it is. So that's what I'm implementing in my code. Q roll again is kind of simple. So it's this combination that we saw before, which is extremely long because I have to do this stupid np.minimum. So if you're at position BCT, then you will add 2 to your current value if you roll again. So 2 or plus 3 or plus 4 or plus 5 or plus 6. I spent about 20 minutes debugging it because I had 1.0 times 6.0 instead of 1.0 divided by 6.0. But that's the right thing. So it's saying, you're going to go up by 2, 3, 4, 5, or 6, 1/6 of the time. And also, one other thing can happen to you. 1/6 of the time, you can bust. So if you roll a 1, then you've gone bust. And the question is, what happens in that situation? And that is the first non-trivial mathematized question. What happens in this situation? What should be written in the busted state? So we're at BC and time T. And so in terms of BC and T, what should go there? And if you understand the rules of the game and how things are working, then it shouldn't be too bad. Any questions or comments? All right, I'll let you guys think for a minute. or two about this. And they are like math things, so it should let you do like formulas. And we'll see if you guys enter the right formulas. Of course, your answer should involve B, C, and T somehow. Maybe I'll give a little bit more time. Okay, 30 seconds left to put in your guesses. All right, 10 seconds. Put in your guesses, even if you don't know. I guess make up a silly number. What's a good silly number? 1, 2, 3. I guess. I don't know. Okay. What did people say? Reveal counts. Okay. 10 people said B for the first one. Some people said 0. Some people said 1. What else do we got? Yeah, I guess lowercase versus uppercase B. Some people said B minus 1. Interesting. In the second one, some people said 0. Some people said B plus C. And in the last one, people said T minus 1 was the most common answer, then T. And I will tell you, in all three of these, the most common answer was correct. So if you said B 0, T minus 1, you got it perfectly right. Let's see, what was the hardest one for people? What was the easiest one for people? Okay, this one. People said 0. This is very good. So if you go bust, you lose your current count. So you go down to 0. That is what happens. So remember, we're trying to figure out what happens when you roll a 1. That's what we're doing. That's the busted value. And it happens 1/6 of the time. That's why it's appearing with a factor of 1/6 in our Q roll again. Our Q roll again is some kind of average. And this is like, what is the value of the situation where you have rolled a 1? And when you roll a 1 at round T, what happens is you go to round T minus 1, and you have 0 as your current thing. So you go back to 0, but you get to keep your whatever you've banked. So that's B. So I guess the trickiest one was the T minus 1. Remember, you've used up a turn, right? You have one less turn to do. So that's kind of what you've used up. Okay, yeah, I don't know what else to say about that. Any questions or comments about the B0, T minus 1? That is exactly the right answer. So let's put that in. So the V of B comma 0 comma T minus 1. And you might notice that 0 is the number 0. But Python will do something called broadcasting, and it'll make sure that everything in here is the same shape as the array B, and so all the slicing will work. Everything will be sort of B-shaped, and B is, remember, this kind of shape, B max times C max. Okay, so that's the busted value. I do want to say one other comment, which is, when we started the course, we did a lot of stuff with matrices, and then you might notice there's no matrix here. That's because we've sort of like hand-coded the matrix by hand. This Q roll again is actually, it's a linear combination of entries in V, and all of the numbers are 1/6. So this line, Q roll again, is some combination of these entries of V, could also be written equally well in terms of a matrix. So you could say Q roll again, I guess in this case, it is 0 plus gamma times M roll again times V. right? So this is like this first one is the first part of the development equation. This is the second part of the development equation. And I guess I'm doing pi star. Let's put the stars in. This is pi star of rolling again. And it just so happens that this matrix, in this situation, there's 6 things that can happen to you. So you could write it out as a 1/6 of v pi star of, I guess what was it, b comma 0 comma t minus 1 plus 1/6 times v pi star of b comma c plus 2 t plus dot 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 all the way up to pi star of b c plus 6 comma t. So it's a linear combination of 6 elements of v, all with the coefficient 1/6. That's like saying this matrix has exactly six non-zero entries in the row. All of the entries are 1/6, and it has it in weird spots. Like it has it in this location, in this location, in this location. If you really wanted to write out the matrix, you'd have this horrendous matrix that would be like, it would have 6 axes, right? Because it would have 3 axes for the input, 3 axes for the output. It would be a real mess to write, but we're kind of doing it without having to ever write it down, which is a nice thing. Okay, so that's it for Q roll again. And you guys have figured out this is the busted value. So if you go bust, you go up to level t minus 1. And this is what I meant when I said, if you know what happens at time t minus 1, it helps you figure out what happens at time t. Because the values at time t depend on the value of t times t minus 1. Okay, great. Back to here. Any other questions or comments about that so far? Okay, so the next thing you got to do is what is the value if you decide to stay? So last class, it was very simple. If you decide to stay and you're at state S, you get S points because it was 1 round. But now there's more than 1 round. So what is the value if you decide to stay? And just like before, that's the next mathematized question. You tell me the Q stay value. And yet, if you have something that involves like np.minimum, don't bother writing the np.minimum. Just tell me the main thing. I will make sure that it doesn't overflow. Okay, I'll give you guys a couple more minutes to work on this one. All right, 10 seconds left. Put in your guesses. Okay. Video counts. Okay. This time, confident majority in B plus C for the first entry, majority in 0, and T minus 1. Very good. You guys got it. So it's B plus C, 0, and T minus 1. I guess the most confusing one was the 0. Right? If you bank your points, then you go, on the next round, you start at 0 again. You get to bank the points, so they get added to your total. Yeah, your sort of current value goes down to 0. So let's put that in over here. So this is, if you choose to stay, then you go to v, b plus c, comma 0, comma t minus 1. And somehow the 0 came out wonky. All right, and again, it's very nice because b and c are arrays technically, but b plus c, totally valid array, and you can do v and b plus c. It's totally, it all just works because of that slicing and indexing I said before. Okay, everything I said is true except for there's one small problem. If you run this right now, it's going to crash and it won't work. Does anyone know what you got to do to fix it? Yeah.
Is it because the math is like a limit on 50, so the c is over because we're going to try to get out of bounds or e?
That's right, yeah. So if b plus c is larger than the largest possible thing you could put in the first thing, then it will yell at you. And it'll say, hey, I tried to access element 51 of something that only goes up to 50. That's not good. So you got to do one of these, the minimum of this and b max. So unfortunately, you have to do a lot of these to avoid these overflows. Again, like in your homework, we kind of think of these games that live on infinitely many states as having a finite upper bound. And now it should work. So, okay, it was dangerous running it without checking. But okay, let's see. Did it output the same thing as before? Woo, we did it. So one thing that's cute, you can kind of see, it kind of makes sense, like the probabilities get closer to 1. Like the more returns you have, the more likely you are to win. Looks good. You can plot it as a function of, in 3 dimensions. So here's your bank points versus rounds remaining. In the 0th round, right, you lose unless you're at 50. And then every round just like depends on the round above it. And so you get these nice pictures of the rounds above it, and you can kind of see this this diagonal is like your line of if you have enough points, you're probably going to win. If you have not enough points, you're likely to lose. And where are you? And then the fun thing you can do is you can figure out where you should roll again and where you should stop. And again, the way you do that is just like you guys figured out last time. You ask the computer, please tell me where is rolling again higher than staying. Where rolling again is higher, that means we should roll again. Where staying is higher, we should stay. And then you can look at these and see what they're like. So yeah, if you have, okay, this is with 0 rounds left. And it's saying, look, with 0 rounds left, the game's over, man. It doesn't matter what you do. Okay. With 1 round left, it's like we said, with 1 round left, you roll it. If you haven't won, this is your last chance. So you just go for it. If you win, you win. If you don't, you don't. Somewhat surprisingly, if you have 2 rounds left, it's the exact same strategy. So even with 2 rounds left, basically you just add up your banked points plus your current points. If it's larger than 50, you're like, yay, stop, I'm going to win the game. If it's not larger than 50, you just keep rolling over and over again, which seems very weird. It's like counterintuitive. It's like, why wouldn't you bank at some point? But yeah, anyone want to, let's think about it for a sec. Why is it like this? I stared at this and I was like, oh, is there a bug? Did I do the code wrong? But it's actually correct. So you got 2 rounds left. Why should you never bank unless you're banking to just win the game? Yeah.
Is it because if you have 0 rounds left, you're going up to 20, and then to 40 is still less than 50?
You're thinking about the 20 thing, right? Yeah. So the 20 thing, right, was sort of a different reward function. The 20 was like we're trying to maximize on average how many points we get. Now we're not worried about that at all. We're like we're just trying to maximize our chance to get to 50. So if we can get to 51 99% of the time, that's better for us than getting to 100% 100 half the time. So it's got nothing to do with the 20. Yeah.
Based on the mathematics, banking wasted turn. So basically, if you're 2 turns away, the second banking wasted a turn, they could roll to get for a better chance of actually reaching.
Yes, that's right. So I mean, by the rules of the game or the mathematics, right? When you bank, you lose a turn, but you gain whatever you banked. But the thing is, we know that from this situation, when t equals 1, we know it doesn't really matter how much you've banked. It matters, can you bank plus get to 50 in the current round. So sort of, if you choose to bank with 2 turns left, then when there's only 1 turn left, you're still going to have to get all the rolls you need to get to 50 points anyway. You might as well just go for it now at 2 points, and then if you fail, you'll get another try. Whereas if you bank, then you've used your bank and you don't have another try. So you sort of, when there's only 2 rounds left, there's no time for banking. You just got to go for it and hope for the best. So whatever rolls you need to come up, they might as well come up here at t equals 2 and help you win the game. There's no reason to bank and then go for them at t equals 1. So because you're just doing this thing at t equals 1, that's why t equals 2 is like that. It doesn't work forever though. So at t equals 3, you do start to bank. And so in fact at t equals 3, you should bank if you're at 30. So if you get to 30, I guess 31. If you get to 31, then you bank. And you save your points and go for it later. And the more rounds you have left, the like, you know, you can be less risky. So when t equals 5, if you have no bank points, you do the 20 strategy. The more bank points you have, the less you need to do. So if you somehow have 40 points, you only need to get like 5 points. And you're like, yeah, I'll take it. I'll bank my 5 points and be at 45, and then I will be happy with lots of rounds left to go. So it's sort of the more time you have left, the less risky you have to be. And then when you have like 1 or 2 rounds left, you're just like maximally risky. You just go for it 100%. Okay, that is the one-player version of Pig with multiple rounds, which is already kind of interesting. You will have a homework problem on assignment 3 that is very similar to this kind of thing of like figuring out what to do or not in these kinds of situations. Questions or comments about the, this is like Pig Solitaire, I guess, yeah.
So the optimal point or bank points doesn't look monotonic. Like, sure.
Is not, what do you mean by it's not? I think it's monotonic. Oh, you mean over here?
Yeah.
This thing?
Yeah.
Yes, that's a great point. So one of 2 things could be happening. Actually, one of 3 things could be happening. One is it really could be not monotonic, which seems weird. It's possible, though. And actually, we're going to see something where we're going to see that in the 2-player game, there are these non-monotonic things that happen. Another thing that could be happening is, and this is quite common, is that they're almost equal. So it's like it doesn't matter if you roll again or don't. The optimal thing is either way. Like they're both exactly the same. They both give you the same chance of winning. And then in our computer, when we said which one is bigger, the computer has some like random error in like the 10th digit, and it's like this one is 0.00001 bigger. So it could be that they're tied. If you wanted to you could make a thing that's like, if they're really close, make it a different color. Make it like 0.5. You could do that. Yeah, sure. Why don't let's do this really quick. Let's say so it's this minus 0.5 of np.abs of the difference q roll again t of bc minus q stay t of bc. So let's see, did I get the brackets right? So that's the absolute value. So if the absolute value is, let's say, less than 0.0001, let's do like 2 zeros, like very close, then we're going to subtract a half. So if you really should roll again, it's a 1. If you really should stay, it's a 0. And if it's like really close, then it should output a half. I wonder if this code will run. Let's find out. Did something. Okay. Oh, 0. Okay, yeah, so here we go. Here are some points where these like little points on the boundary, where it's like yellow or dark blue, that's like a tie. So it doesn't matter what you do, it's like almost the same. And I guess the one you were interested in was this one. Okay, well I don't know why it's sometimes negative. Oh, okay, that means you should stay and it's close. Okay, great. So yeah, all right. Well, okay, I don't know, you could fix it if you want, but it's something like this. Okay, so yeah, so these weird non-monotonic parts, it's like really close, too close to call. Okay, great question. And yeah, something you have to worry about when you do these maximums is, do we really care if it's bigger, if they're within like 0.001 of each other? Okay, great question. Any other questions or comments? All right, so the next thing we're gonna do like very briefly is the 2-player version. We're mostly just gonna watch the YouTube video, but let's work it out quickly. And because there's one trick about 2-player games that you must know to be able to set these things up if you ever want to do a 2-player game. All of your homework problems for now will be 1-player games. Your final project might be a 2-player game. Okay, what to do in 2-player games? So we'll do 2-player Pig. Okay, and last class, I had you guys say, what do you think the states are in 2-player Pig? So for 1-player Pig, we had B, C, T. That was the 1 player with T rounds. In 2-player Pig, what is the state? And a lot of people voted for 4 things, and I said 4 things is not correct. It is not 4 things. So what should the state be, and how many axes should it have? Anyone have a guess? Yeah, Gabe. 3. Okay, what are the 3?
The bank total of player 1, bank total of player 2, and the current total.
Very nice. Okay, so we're gonna say B. So how should we do them? Let's call player 1 Alice and player 2 Bob, so that they can be A and B. It was player 1, and Bob is player 2. And you're gonna have A, which is Alice's banked points, banked. You can have B, which is Bob's banked. And then you have, what was the third one? What was it that you said?
The current total.
The running total, like so far, yeah. Okay, we'll call that C like last time, so the current amount. Okay. All right. There is one thing that is left off of this state space. So if you try to do it like this, you can make it work. You got to think carefully and do some tricks. But there's one other important thing that needs to be there. Yeah.
Do we have to account for whose turn it is?
Whose turn is it? Exactly. So in 2-player games, you must always, or in 2-player games where people take turns, you always have to add in a whose turn is it. And whose turn is it will be like, instead of being a whole axis, like being all numbers, will be either 0 or 1. So whose turn is it? Whose turn? And this is quite annoying. So what I'm going to actually show you is how you can get away without keeping track of whose turn. And there's one little trick that you can often do, and it works in games that are symmetric. So as long as the game is symmetric between Alice and Bob, there's a trick by using symmetry that you can do, so you can eliminate this whose turn thing. And the trick is you always think of the value from the point of view of the current player, and by symmetry, the situation for the other player will be 1 minus that. So this is the trick. This is the symmetry trick. The symmetry trick, which is, so let's let V of A, B, C be the value to Alice when Alice has A, Bob has B. These are banked, I guess, banked. And it's Alice's turn, and C current. So we're taking the point of view of Alice. We're saying it's Alice's turn, and she has C points on the go. So the situation is that if it's the value for Alice to have A, Bob to have B, and there to be C points on the go, if you look at the value to Bob, then the value to Bob on Bob's turn, so when A equals Alice, B equals Bob, turn equals Bob's turn, and C equals Bob's current. So this one was all Alice, right? Alice was over here. Let me label this with Alice. So Alice had C. It turns out you can also figure this out. So even though this is Bob's turn, and I only made the function V contain what's going on Alice's turn, there's a clever trick you can do, which is it's going to be V of, okay, I'll leave, the C is over here. Does anyone know what I should do with the first 2 entries? Yeah.
Do we swap them?
You swap them. So what you do is you just like relabel Bob to Alice. You like take off their name tags and swap them. And so what it's saying, like this situation is exactly the same as the other situation, except you just have to switch like what you put in. Okay? And this is the value to Bob. And therefore, so this is like this is a true statement. And there's one other statement which is important. So this is helpful. One other fact, which is that the value to Bob equals 1 minus the value to Alice. So if you ever want to know, like in a certain situation, if you know how valuable it is for Bob, you can figure out how valuable it is to Alice, because we're talking about the probability of winning the game. One of them is going to win, so it always satisfies this. Note that not all games satisfy this, right? So like in chess, for example, there's ties and things, like it can be more complicated. In real life games, there's no reason the sum is conserved, like maybe you can work together and like both get a better outcome. So this is called a zero-sum game, a zero-sum game. So it only works for zero-sum games. But if you have these 2 things, you can come up with the equation. So I will kind of quickly show you the equation. We won't solve it, and we will just go from there. So what do I have to do? I have to figure out the Q functions. There's Q stay and Q roll again. And again, I'm going to take Alice's point of view. So A, B, C, and it's Alice's turn. And Alice's value. That's what we're doing over here. Okay, so Q stay. So if Alice is at A, B, C, and Alice chooses to stay, like to stop rolling, then we're going to add the C to her point total. So it's going to be A plus C. Actually, let me write it out like this. So if we stay, then what will happen is it will be three things will happen. It'll be A plus C will be Alice's total. B will still be Bob's total. The runners will go back to 0, or the current amount. And it will switch to Bob's turn. So the turn is Bob's turn. So that's what happens when Alice chooses to stay. How do we write this one down? Well, because it's Bob's turn, we're going to have to do a swap. So we're going to swap B with A plus B. And we want to make sure we represent it from Alice's point of view. So there's going to be a 1 minus. So if you choose to stay from, say, A plus B, A, B, C, what you will actually get is 1 minus V of B, A plus C, 0. Which looks very funny in the code when you see it. So the things reset, and we sort of swap points of view, which gives us a 1 minus, and we swap the B and the A plus C. This is like kind of trippy if you don't think about it, but if you think about it a little bit, it's not bad. You could also include Bob's turn in there and then just like avoid all this stuff, but this is normally how people do this stuff. Questions about that one? Just like that's like the value when we stay. Okay, what happens if we roll again? Okay, so if we roll again, well, 1/6 of the time we go bust, so we got to figure that one out, the bust value. But the rest of it isn't so bad. So in this situation, you do A plus 2, B, oh, sorry, not A plus 2, C plus 2. B, C plus 2, plus 1/6, V of A, B, C plus 3, plus ... all the way up to V of A, B, C plus 6. Okay. So this part is normal. You're just adding to the current turn totals by 2 through 6. The hard part is maybe the bust value, because that one again is like this funny reverse thing. So the bust value from state A, B, C, again, it's going to be a 1 minus, and you've gone bust. So it's just V of B, A, 0. So that's the bust value, right? So you don't get anything added to your total. The current total resets to 0, but now it's Bob's turn. So you swap them, and you do a 1 minus to represent the fact that we always want it to be in terms of Alice's point of view. Okay, so that's like how you would set it up. You write the same code and do it again. The reason I'm not going to do it is because there is a paper that someone published that just does this, and that's what they talk about in the pig video. So I'm
How valuable those positions are. They're all interconnected. They set up.
See, this is right. This is exactly what we've been doing. So P, that's the matrix. It has P superscript A. It depends on the action you take. That's the Bellman equation. This is the value iteration algorithm. I'll show you this. It's exactly the same as it appears in the textbook. They did some funny thing here. They have this delta. They're keeping track of how much are the values being updated, and they're like, keep updating it until the updates are small, right? Once the updates are really small, just stop doing it. We've been doing it like some fixed number of times. It's basically the same thing. Yeah.
In our version of the Bellman equation, the matrix only multiplies the value function. In the papers, it's multiplying the value function and the reward.
Yeah, right. So that's because, do you remember we had the reward vector, which is the expected amount of reward that you get. How do you find the expected amount of reward? Well, you multiply by all the probabilities and add it up. Yeah. So over here, if you were to split this thing into 2 parts, one part would be R times P. If you add up all those, that's the expected reward. And the other part would say gamma times the sum of P times V. And that would be the matrix P applied to V. In this particular game, there are no ongoing rewards. So R is 0. In a lot of games, the rewards are like non-random, like you always get 1 or something. So it's kind of helpful to split it off in our Bellman equation. Yeah, great question. You'll have a homework problem that has both. That'll be coming up. Okay, so yeah, you need to know both. Okay, questions, comments? All right, let's keep watching for.
and total that you're currently on, the one you have control.
Okay, so we called this one A, we called this one B, and we called this one C. And for every A, B, and C, you either should roll again or you should stop, right? So just like my pictures before, there were two colors, or they were two colors, either red or blue. Every little box here is either filled in gray or it's blank. And that tells you where you should roll again or where you should not.
Control over. And that's because
Does anyone know why the plane is there? I guess he's about to say, but I will ask you. What is this weird plane? I'll give you a hint. If it's filled in, that means you should roll again. If it's not filled in, that means you should stop. Yeah.
You were in enough.
Yes, exactly. So this plane represents the situations where your score plus the total you have in the current round is large enough that you'll just win the game if you stop. So it's first to 100. If you're ever in a situation above this plane, you've already gotten to more than 100. Just stop and win the game. Why are you risking? Don't take any more risks. Yeah.
So in the graph that you showed, what does the gray reachable mean?
Oh yeah. Okay. That's a good point. So we haven't talked about this yet, but so when you follow the optimal strategy, there are some situations that you will never encounter. So for example, if your strategy is I'm only ever going to bank if I get to 20 points or more, then it's impossible to bank a 10 because you would re-roll if you're at 10. And so what this gray region is showing is that if you are playing the optimal strategy, like you will never bank a set of points less than 20. So you will never have a point total that is less than 20 if you're playing optimally. This is a bit like, I don't know if you guys have ever been around like kids chess tournaments, but you like walk up to a game and like both kings are in check. You're like, these kids, they've done something wrong. So it's the same thing if you are watching people play pig and somebody has 14 points, then you know they did something wrong. Yeah. Yeah.
What's like the second gap?
The second gap, this little one?
Yeah.
I guess what they're saying is that when people are playing optimally, you will never have a situation where this player has this many points and the opponent has 30. I can't think of the reason why that would be, but it's got to be some kind of combination of like, well, you would never have less than 20. If you're at 20, then you would at least get another 20. So like, there's some regions you skip over. I can't tell you why that one is there in particular. Yeah, that's a good point. But yeah, and then, so the other thing that they were pointing out is that there are these overhangs, right? Where if your turn total, your current amount is big enough, then you should keep re-rolling because you're close to winning the game. If your turn total is medium-sized, you should stop because you have a pretty good total. If your turn total is small, you should re-roll. So it goes from re-roll to stop to re-roll as you get more points. Just because if you get enough, you just win the game immediately, and the risk of letting the opponent have more turns to catch up is not worth it. You should just go for it now. So that's interesting. It kind of like incorporates the risk aspect of it. All right, any other questions about that one? Okay, so let me show you in the textbook what we've been covering. So this is one of the free, this is like the famous reinforcement learning textbook that is free online, and we've done this value iteration algorithm, and it's for estimating the optimal policy pi star. And so this is called value iteration. This is in their chapter on dynamic programming. This is what they call it. And let's see, what else did I want to show here? Oh, okay. So this name, the name of what we've been doing, is sometimes called policy iteration. And what we were doing before that is sometimes called policy evaluation. All the way back here is policy evaluation. So policy evaluation says, if you give me the policy, can you tell me how good the policy is, right? Can you find the v function, the value function, for some fixed policy? That's really what we were doing in the first couple weeks before we had any actions, right? Because once you fix the policy, there is no choices to be made. And then the second thing we were doing was really policy improvement, which is policy improvement is when, can you improve the policy? And you can really think of when we were doing our value iteration, you can think of it as alternating these steps. So you can have this sequence of you have some policy pi, you evaluate how good it is, you find v pi, and then you improve it to find pi 1, and so on and so on. This is what we were doing because we had our two equations, right? So let's see, where were our two equations? I'll just write the two equations out again. So right, we had these two equations. We had one equation that says v pi is the maximum over all the q's, q pi. And we had one that says that the q pi of SA is r call it R of SA. Okay, R of SA. The expected reward plus gamma times MA times V pi. Okay. And so this line over here is saying for the current policy, the value is the best possible choice you can take. And this one you can really think of as improving the policy. So if Q is a really accurate estimate for the current values, then this tells you the best policy. This is policy improvement. Improves the policy. And maybe this is like the hidden line that isn't written here that we talked about, is that actually when you're doing this thing, you're also doing the argmax, right? The optimal action that you would pick is also this. So the best possible action you can pick is given by this line, and we hope that the Q's are an accurate estimate of how good all the different things are, and if they are, then this will be the best action we can take. So this improves the policy. And this policy over here, this is sort of implicit. If you know the Q function, you know this special policy of choosing the action A. I guess I shouldn't write A. Like you could also write this as pi of S, right? What should you do in state S? This is also called the greedy policy. Greedy policy. And it's the greedy policy because it always does whatever we think is the best at the current time. So whichever Q value is the best, we will try that one. And so what we're doing is we're doing greedy policy improvement by always doing this in our thing. And then we evaluate, this is the Bellman, this is like the meaty part of the Bellman equation. This is like update Q based on V, right? So we figure out if we can find a good policy, then we can see if it's really accurate. We can get more accurate estimates for the Q functions by using this. So this is like policy evaluation. Policy evaluation. Okay. And so you can really think of what we've been doing with these two equations as a sort of a chain of alternating these two steps. Where did my thing go? Right? So we start with the sum policy, we calculate V pi, then we do this, like, choose the best thing you can, that gives you pi 1. We figure out how good it is, and over and over and over again, and this will slowly converge to the best possible value function, and therefore the best possible pi. So that is value iteration. And okay, there is one other example I was going to do, which maybe I will record or do something like that, or maybe we'll do it next class. And it's called the gambler's problem. And this is also in the textbook. This is a nice problem. The reason this is a good problem is so far we have done an example, pig, in a lot of detail, where there were 2 actions. You either hold or you roll again. But in real life, you might have many actions. And in the gambler's problem, it's an example where you have many actions like that. So I guess I'll read it. So a gambler, I also like to call this how to gamble if you must. So a gambler has the opportunity to make bets on a sequence of coin flips. If a coin comes up heads, he wins as many dollars as he has staked on the flip. If it tails, he loses. The game ends when the gambler wins by reaching a goal of $100 or loses by running out of money. So this is a kind of a funny situation. Normally when you're gambling money, you're trying to maximize the amount of money you have. But this gambler is not like that. This gambler owes $100 to the mob, and so if he can leave the casino with $100, he will be fine. Otherwise, he will lose. Okay? So you get 1 life point if you get to $100, and you get 0 life points anything other than $100. Okay? So you have to gamble, and you have to get to $100. Having $99 is the same as having $1, is you lose. Okay? You got to get to 100. This is very important. And what are the choices you can make? You can choose how much you want to bet on each flip. I will, let's draw a picture of this. So here is $0 over here, $0. Here is $100. And you can think of all the possible dollar amounts in between as being kind of a ladder. And here you are, maybe you start the game at, let's say you start the game at $50 in the middle. So there you are, your bankroll is at $50. And you're going to choose how much you want to bet. Let's say you bet $1. Well, if you bet $1, you will either go up to $51 half the time, so the probability is half, or whatever the coin flip amount is. You'll go up to 51, or you'll go down to $49. Okay, and remember, if you get to $100, you win, you're happy. You're going to stay in the casino until you get to $100. So if you ever get to $0, then you go broke, and then the mob comes in and does whatever they're going to do to you. So you don't want to do that. Does this remind anybody of anything? Yes, this is the drunkard's walk. There is one difference between this and the drunkard's walk. What is the difference? Yeah.
You can move more than 1 square.
You can move more than 1 square. So in the drunkard's walk, you always move 1 square. In this one, because the amount you move is however much you chose to bet. So you get to choose your actions. The action is choose your bet size. Choose your bet size. So if you always choose to bet $1, then it's exactly the it's exactly the drunkard's walk, always steps of size 1. But you could say, I'm going to bet $10. And then you would go up to 60 or 40, down to 40. So the thing that is hard is that choosing the bet size is more than 2 values. So choosing the bet size could be anything between 1 and 100. So there's 100 possible actions in this game, and that makes it more challenging to sort of implement on a computer. But again, a little bit more realistic. Yeah.
Do you have to gain 100 from wherever you start?
You have to gain 100 from wherever you start, but not necessarily in one bet. So you can make you can bet and then see where you end up. But your goal is to maximize the probability that you make it to 100 at some point.
Okay.
Which is why I call it there's a famous book called How to Gamble If You Must. How to Gamble.
So I'm guessing the optimal strategy is not to just bet $50. Get that 50-50.
It depends on.
I guess it depends on the probability.
It depends on how good the coin flip is. So it turns out if the coin flip is 50-50, then it doesn't matter what you do. It'll be 50-50 no matter what, which is interesting. If the coin flip is good for you, like you're more likely to win than not, then you should always bet $1. And if the coin flip is bad for you, you should do what you're saying, which is always bet all your money. But we'll see next class. Yeah. We have a question over here.
I was just wondering why actions from 1 to 100.
Oh, I guess you can bet any amount of money. I guess it should be 1 to 99. Would that make you happy?
Well, if you're at, like, shouldn't it be
Wait, so
50?
Yeah, okay, this is a good point. So 1 to 99 are the available actions for all the states. And this is another example of a game where not every action is available in every state. So the set of all possible actions is 1 to 99, but the set of actions available at state S are only 1 to S. So when you have S dollars, you can bet a maximum of S. And actually, this is quite annoying in the code. So this is another reason this is like a good example as to how do you deal with this issue of some actions are only available in some states, other actions are available in other states. How do you code that into your computer? We haven't seen an example like that yet. Yeah, great. Any other questions or comments?
We just clarify.
Yeah.
We owe 100, but that doesn't mean that we're not trying to increase our current profit by 100. We're just increasing it to 100.
That's right. We get 1 life point if we get to 100. We get 0 life points if we get to anything less than 100. So once again, we're going to have that value function at the final, the thing anchoring everything. It's going to be all zeros and then all ones, just like in trying to win the game in Pig.
Yeah, I guess I was just confused by the model reference.
Right. Well, so yeah, that's the way you should think about it. Is we need $100 for a thing, and we're trying to maximize the chance we can get our thing. Right.
We need this, but we have this.
That's right. We need $100, but we only have $50 to start, and we're going to go to the casino and hope for the best. Okay. Okay, we'll do that one next class, or I'll record or something.